Hello students! So dahil nakamiss tayo ng isang DC class, bibigay ko sa inyo itong video lecture for our DC 2-4. So today mag-start tayo with a problem on method of images as an exercise since napakaganda na itong topic na to. So might as well we put our mastery on this topic. Next, I'll give you an overview on the semiconductors, then we will proceed with a problem on boundary conditions for dielectric materials. And finally, let's have a problem about capacitance. Unlike resistance and soon the inductance, capacitance is a very critical component in every aspect of electrical engineering. So now let's proceed with method of images. Now we're given an infinite line charge, say rho L plus, equal 25 nanocoulomb per meter na nasa x equals 0, z equals 1. Then, meron daw tayong perfect conductor at surface z equals 0. So, using method of images, we can remove this perfect conductor and replace, add an image for that rho L positive. Let's name it negative 25 nanocoulomb per meter. The location, of course, if it's an image with respect to the z equals 0 surface, that's x equals 0, z equals negative 1. This is the image of this with respect to sa z equals 0 na surface. And we know electric field given a line charge is equal to rho L over 2 pi epsilon naught rho A rho hat. That's for volts per meter. Okay? So given these two line charges, using superposition, we can find the total electric field at point P. That's 25 nanocoulomb per meter over 2 pi epsilon naught. That's for the positive. Therefore, the rho with respect to point P is, that's 3 minus 1 squared plus 1 squared times the unit vector, represent natin sa rectangular coordinate system, ax hat plus 2 az hat all over magnitude na itong dalawa. That's square root of 5. Plus, yung contribution ng negative na line charge. Plus negative 25 nanocoulomb per meter over 2 pi epsilon naught times, then, nandun tayo sa negative na line charge, therefore yung rho natin papunta dun sa point P. So still, that's 3 plus 1 squared plus 1 squared. Then the unit vector, that's ax hat plus 4 az hat all over square root of 17. The total be in volts per meter. So, lahat given na, then I can compute for the total electric field at point P. That's 63.4 ax hat plus 74 az hat volts per meter. So that's the electric field at point P.
Okay, got.
Now let's find the potential at point P given na V equals 0 at the origin. So the formula for potential difference, as we know, is the integral, line integral of the electric field dot dl from B to A. So at point P, say BPO equals BP minus VO. So, yung electric field natin, contributions per each dun sa positive line charge saka sa negative line charge. So, by superposition, pwede natin pagsamahin line integral for rho plus equals 1, and then rho plus up to square root of 5. So y, 25 nanocoulomb per meter over 2 pi epsilon naught rho plus. So that's a variable. And our line integral is d rho. Plus, yung contribution ng negative na line charge. 25 nanocoulomb per meter over 2 pi epsilon naught rho minus. That is rho minus from 1 up to rho minus equals square root of 17. And again, the line integral, or the line differential is 0. So like our previous problem, itong rho plus equals 1 na to, and then rho minus equals 1 na to, naka-reference dun sa surface natin, perfect conductor. Thus, itong negative na to, negative nito, plus negative times negative, so positive, magka-cancel lang itong dalawang ito. Therefore, ang lalabas lang dyan, take out ko yung constant na lang, 25 nanocoulomb per meter over 2 pi epsilon naught. Then integrate d rho over rho, that's just ln rho. And working yung mga signs nila, that's from square root of 17, this one, to square root of 5, this one. So again, plug in na lang. Then, since 0 yung voltage ko sa origin, BP equals 275 volts. So, that's the final answer. Moving on to the next problem, we were asked about the surface charge density. So, how to solve for that? Remember Gauss' law? Yes? So, the conducting plane now will be our Gaussian surface. So, since our E effective is composed of function of rho L plus and rho L minus, we only need to find the normal component of this electric field to that surface. We know from Gauss' law that Q equals D that ds. Okay? So the E normal to that plane will be what? That's the contribution for negative AZ hat and positive AZ hat. The negative AZ hat is contributed by the positive charge, line charge. Times negative AZ hat plus the negative line charge per meter. The distance is 1 with positive AZ hat. This is normal to that surface. And then again, plug in lang. We'll get a value of 899, negative 899 AZ hat volts per meter. So how to determine the surface charge density from here? Well, that's easy because this electric field, and we know the magnitude of rho S max is just the normal component, but this is already the normal component. So just obtain normal component ng electric flux density that's equal to epsilon naught, assuming free space, En. Then we'll get positive value, absolute value, 7.96 nanocoulomb per meter squared. So again, since ito na yung normal dun sa surface na yon, ito na rin yung mag-represent nung surface charge density, as indicated na rin nung Gauss law. Oh, surprise! Today we'll have quiz 2-4 to test our understanding. Please try not to look to your notes or to your books, but syempre, wala naman nagbabawal sa inyo gawin yun. Here, we're given the potential field, and then solve for the following. Here are the answers and let's take a closer look. Check your own papers with a maximum of 10 points. If you fail to get the correct answer, please try to work on it again. I will give the solution at the end of this lecture. Our next problem is on semiconductors. For semiconductors, we have two current carriers present. These are the electrons and holes. So next problem is on semiconductors. We know yung electrons and holes, they both have the same amount of charge. Negative yung sa electron, positive dun sa hole. So 1.6022 times 10 to negative 19 coulombs. Well, yung mga advanced na calculator, meron silang provided na constant for that unit of charge. And we're given na yung concentration natin, both for electron and holes, ay 2.5 times 10 to the 19 per metric cube. And then, to identify their charge concentration, since may charge na tayo dito, then yung concentration per metric cube, we can get that right away. So that's negative 1.6022 times 10 to the negative 19 coulombs times nung concentration ng electrons. Then we'll get negative 4.01 coulomb per meter cube. Similarly, yung hole natin, positive lang nung sa concentration ng electron. So that's positive 4.01 coulomb per meter cube. Then for conductivity, since yung current carriers natin, parehas nagko-contribute yung electron and hole, i-take into consideration natin pareho. So conductivity for semiconductors is negative mu E times rho E plus mu H and rho H. Therefore, yung conductivity natin, function ng mobility and charge concentrations for both electron and hole. So, plugging in, given naman na tayo ng mobilities. So, this is sigma, equal to 2.8 Siemens per meter. And then the other term, resistivity, that's just 1 over conductivity, which is equal to 0.357 ohm meter. And then yung next quantity, resistance, given na tayo ng resistivity. Resistance is just a function ng geometry ng material. So that's R equals resistivity, that's ohm meter times length over area. So equals 0.357, then metric tayo, yung 1 cm, 0.01 times yung surface area. Right away, that will give us 892.5 ohms. So this problem is very easy. Next, we'll look at the boundary conditions for dielectric materials. As I've said before, dielectric materials have the ability to store electric energy, and we'll use here the concept of relative permittivity or dielectric constant instead of using epsilon naught if we are assuming free space. So now we're presented with a problem na meron tayong dalawang dielectrics. So paano yung mga boundary conditions for those conditions? Well, actually pwede rin dielectric plus conductor. So now, the boundary conditions for dielectric material says that with respect dun sa boundary, well, based sa problem natin, sabihin natin this is x equals 0. This is the x-axis. Then, this is region 2. Given ng relative permittivity epsilon r sub 2. And here, region 1, that's just free space. Meaning yung relative permittivity niya equal to 1 lang. So with respect to the boundary conditions for dielectric materials says that the normal components of the electric flux density, normal components are continuous, as well as the tangential components of the electric field. Continuous. So, given tayo ng incident dito, say this is D1, since iba na yung property ng next material, boundary condition, this is the boundary. So, let's define this as boundary. Since iba na yung property ng next region, magkakaroon ng parang refraction yung electric flux natin. But still, these conditions should hold. So D2, that's theta 2, and from here, that's theta sub 1. So the x components is the x-axis, are normal to the boundary, meaning the y and z are tangential. So given tayo ng d sub 1, that's 15 ax hat minus 20 ay hat plus 30 az hat. Mamaya na natin lagyan ng units. Then, electric field ng 1, that's just 15 over epsilon naught, since electric field ay electric flux over epsilon naught. Ay hat, similarly, 30 over epsilon naught az hat. And then we say that yung tangential ng electric field from region 1 equal lang sa tangential field ng electric field ng 2. So, since yung tangential components natin ay yung y and z, equal lang yon. So, well, sabihin mo natin, ex2 yung sa ax hat component. And then yung y and z component, parehas lang. Since sila nga yung tangential. Then sabi rin natin, yung normal components ng electric flux density ay equal. So yung, yung normal ay yung x component. So 15 ax hat plus, hindi natin alam sa ngayon yung tangential. Since sabi lang sa boundary conditions, yung normal components yung equal. So let's designate those as dy2 ay hat plus dz2 az hat. But we know that these are related by d2 equals epsilon naught times relative permittivity, ito yung effective permittivity nila, times electric field nung 2. Then, may correspondence yan. Nakikita natin na yung ex2 equals sa 15. Nung ex2 na to, equal dito. Related by this function. So, ex2 equals 15 over epsilon naught er2. So, that's equal to 6.25 over epsilon naught. And also, pwede natin ma-determine itong dy2 and dz2 since may value sila dito. So, dy2 equals negative 20 er2. That's negative 48, and yung dz2 ay 30 epsilon r2, which is 72. Therefore, we have a final expression for the electric field at region 2. So, 1 over epsilon naught, 6.25, ito yun, na-compute natin kanina, ax hat minus 20 ay hat plus 30 az hat. So that's volts per meter. Okay? So the next questions are very easy since may information na tayo nung lahat ng components nung electric flux density. So finding theta sub 1 first, using yung concept ng dot product, that's d1, that ax hat from the definition of dot product, this is equal to the magnitude of D1 times magnitude ng AX hat, but this is just 1, times cosine theta sub 1. Dot product ng D1 sa AX hat, that's just 15. And magnitude ng D1, that's 39.051 times cosine theta sub 1. Then right away, cosine inverse theta sub 1 equals 67.41 degrees. And similarly, using D2 for theta 2, you can solve for it. So, that's 80.17 degrees. So, sa problem na to, wala namang strange dito sa ganitong problem. So, as long as we adhere dun sa mga boundary conditions, we can solve these kind of problems. So, kahit magdagdag pa ako ng mga regions, basta at boundary conditions, ganito yung conditions. Dapat continuous yung normal component ng electric flux density, then continuous din yung tangential component ng electric fields. The last problem we'll look at is for capacitance. The parallel plate capacitor is the most basic configuration that we'll use to appreciate the concept of capacitance. So, capacitance, by definition, is the capability of energy storage in electrical devices. So, well, the unit is farads. Na-make nyo naman yan sa EEE 34. And we know C equals Q over V sub naught. And Q equals E dot ds, well, epsilon dot ds. And yung potential ay line integral ng electric field from negative to positive potential, increasing. So here, we can see na parehas lang function ng electric field. So kapag yung charge density natin nag-increase by factor of n, so charge density increases by a factor of n, then by Gauss law, alam natin yung electric field or yung electric flux density nag-i-increase lang din ng factor of n. Meaning, itong Q over V naught na to, yung ratio nila is constant. So that's why itong problem na to, present natin yung parallel plate capacitor. Nalaman natin na yung capacitance ay function lang ng geometry ng capacitor natin and the dielectric. So given C equals epsilon S over D. So I hope na derive naman to sa lecture. So given ang configuration A, we can already suspect that this configuration is in series, right? While the configuration in B is in parallel. So given that, for configuration A, kunin muna natin yung capacitance ng mica capacitor. That's just the geometry. So yung permittivity, epsilon naught, epsilon R, times 5 over 100 squared. So that's the surface area over nung distance. So 0.01 over 100 times 2 pa. Kasi kalahati lang yung na-occupy niyang length. So this gives us 0.531 nanofarad. And again, same procedure. Makuha natin yung capacitance ng air given those that configuration. This is equal to 0.0885 nanofarad. And since series yan, we can tell that yung capacitance, total capacitance ng configuration A is, well, the sum. Series sum ng capacitance. which gives us 0.079759 nanofarads. And then the energy stored in this configuration, given 50 volts na potential, we can use the formula 1/2 CV squared. We know the capacitance, we know voltage, then we can get the energy stored. So yung energy stored na to, same lang dun sa formula na ginamit natin dati. Yung may squared nung magnitude ng electric field. Microjoules. So these are the answers for the series configuration. And now, we move on dun sa configuration B. Then again, kunin lang natin yung individual na capacitances, tapos saka lang natin i-apply yung parallel capacitances. So, natin let's see Mika. That's epsilon naught, epsilon r, 5/2. So, nahati na kasing surface area, 100 squared. 0.01/100. So, yung distance naman dito, nakuha niya yung buong distance. Okay? So, this is 0.133 nanofarads. And again, yung capacitance ng air, epsilon naught, 5/2 times 100 squared, 0.01/100. Which gives us 0.0221 nanofarads. Therefore, the total capacitance for configuration B, yung parallel capacitances lang. So that's just C Mika plus C air, which is equal to 0.155 nanofarads. Then same potential 50 volts, can use 1/2 CV squared. That gives us 0.194 microjoules. So, question. Paano malalaman kung series or parallel yung configuration ng parallel plate capacitors natin? Well, actually, na-derive yun sa boundary conditions. So, kaya nasabing itong configuration na to, may kita natin na series to, while this configuration is for parallel. Okay, balik tayo sa concept kung paano malalaman kung series or parallel yung configuration. So, unahin natin yung sa series. Pwede tayo mag-assume on any dun sa conducting plate na meron tayong charge na Q. Then right away, kung may Q tayo, meron tayong surface area, makukuha natin yung surface charge density. That's Q/S and D. And by boundary condition, we know that dN1 equals dN2. And electric field 1 equals D/epsilon 1. Or, gamitin natin yung charge, epsilon 1 S. And similarly, yung electric field dun sa 2, that's D/epsilon 2, which is Q/epsilon 2 S. Parehas lang yung surface area nila. Then we know V1 is equal to E1 D1. This volts per meter times meter gives us volts. Plug in natin Q/epsilon 1 S D1. Then similarly V2 E2 D2 equals Q D2 epsilon sub 2 S. Then sa ganitong configuration, ina-assume natin na merong potential difference between two conducting plates na V0. Therefore, we can conclude na itong nasa isa ay V1, ito ay V2. That is V0 equals V1 plus V2. So, given na tayo ng V1 plus V2, then may mga charge na ring component doon. Right away, yung C equals Q/V0 natin, nakikita natin 1/D1 epsilon 1S plus D2 epsilon 2s. And this formula gives us yung formula for series capacitance plus 1 over C2. That's series. Well, ang kailangan nyo lang tandaan, yung hint, lagi tayo nag-assume ng potential difference dun sa conducting plates. So, kaya itong component na to, kaya siya naging series, kasi ang contribution niya lang ay V1. Then, kailangan pa makuha yung V2 para to sum up dun sa V0. Next, punta naman tayo dun sa parallel na configuration. So, by boundary condition, alam natin na yung E1 equals sa E2. And kung ito ay may V0 din, yung E1 ko, or E2, equal lang, that's V0 over D. And evaluating yung electric field 1, that's just D1 over epsilon 1. Then yung electric field ng 2, that's D2 over epsilon 2. This is Q1 over epsilon 1 S1. Q1, ina-assume ko meron tayong Q dito, charge. Then Q2 dito. So kaya different yung surface areas na kinoconsume. So yung E2 ko, that's Q2 over epsilon 2 S2. And since nag-assume ako ng charge na Q1 dito and charge na Q2 dito, the total charge hence is Q1 plus Q2. Given this formula, that's epsilon 1, electric field 1, epsilon 1, S1 plus electric field 2, epsilon 2, surface 2. Then, alam ko electric field 1 tsaka electric field 2 equal lang sa V0 over D. Hence, this is V0 over D, epsilon 1, S1 plus V0 over D, epsilon 2, S2. Then, balik tayo sa formula ng C equals Q over V0. Q over V0, kunin lang V0. Lalabas dito ay epsilon 1, S1 plus epsilon 2 S2 over D. Since pares lang yung distance nila. And this is actually parallel configuration for capacitance. Parallel. Okay? And now here's the solution for quiz 2-4. Now here's the solution for the quiz 2-4. So first problem, you just need to identify the electric field at the Y component. So given ang potential field, that's easy. Kunin ko lang yung partial derivative ng potential with respect to Y. Since Y naman yung kinukuha natin yung electric field component. Vector AY hat. And with math 54, 53, or whatever, you easily get this. Negative 10 times x to the 3 plus 5 AY hat unit of volts per meter. So that's easy. So next, it's more easy. We have potential of 0 for any point na y equals 0. Well, it is directly given dun sa potential field natin. Pero actually, pwede nyo rin evaluate yung V equals negative E dot dl given na yung paths natin, yung endpoints kung saan natin i-integrate itong electric field na to ay naglalay dun sa y equals 0 plane. So the endpoints should lie on the y equals 0 plane. And still, we have to get v equals 0. Okay? The next, we have q equals d dot ds. again, we already have an electric field effective. So we just need to identify the normal component of this electric flux density to that surface in question. So where ds is equal to dx dz ay hat. Since yung surface natin nandun sa y equals 0. So right away, we have q equals epsilon naught ey, given naman na sa atin yon, dx dz ay hat. Then dx natin ay from 0 to 2 and dz from 0 to 1. So yung electric field natin na y component, function lang naman ng x. So integrating dz and this 0 to 1, so 1 lang yon. Right away, integration gives us negative 1.24 nanocoulomb. So walang mahirap dito. Once na nakuha na natin yung electric field na effective, kaya na natin kunin yung amount of charge or perhaps yung kanina, surface charge density. Pwede natin malaman kung alam na natin yung electric field and hence yung electric flux density na tumatama dun sa surface na yun. Parang titreat lang natin yung conducting surface as our Gaussian surface. That's the end of my video lecture. Please submit your homework 2-3 and your self-check quiz 2-4 next meeting. Please read more on more capacitance examples and make an advanced reading on steady magnetic fields. See you next meeting. Happy Chinese New Year and enjoy your weekend, kids. Goodbye.